Hi everyone, welcome back to Dave's Math channel. I'm your host David Tare, and this is my third video on a series on probability and statistics. Today I'm going to talk, this is part three, I'm going to talk about normal distributions today. And these are very important distributions, and I'm sure you guys have seen them. I mean, these occur all over in the sciences. It turns out that it's a very, very common type of distribution. And here's an example. And this is also, it has other names. It's called the bell curve, or it's also called a Gaussian distribution. The guy who discovered it was a very famous mathematician, Carl Friedrich Gauss. He discovered it in the early 19th century. He even discovered a formula for this curve, which I'll get to in a few minutes. But anyway, this is kind of what it looks like. And, it has a very characteristic shape, and you can even determine what percentage of the area under this curve lies within, a certain number of standard deviations. So it turns out you can, there's a thing in math called the standard deviation. I'm not going to get into that today, but whenever you have a distribution of a one variable, there are statistics associated with it. Uh, the two most common are the mean and the standard deviation. So this would be a normal distribution I'm showing here with a mean of 1150. That's M. And the standard deviation in this case is 150. So then you can, with a normal distribution, you have 68% of your data lying within one standard deviation. Sometimes people write with SD. So 68% of your data is between M minus 1 SD and M plus 1 SD. Or if you like, 34% is between M and M plus 1 SD, or M minus 1 SD and M. So about 68% of your data, about two-thirds of your data lies within one standard deviation. About 95% lies within two standard deviation, two SDs. About 99.7, which is virtually all of your data, lies within three SDs. So when you have a normal distribution, it's very unlikely that you have a data point that's more than three SDs away from the mean. Sometimes people throw data like that out. They say they're outliers. But anyway, and why do we get these distributions? Why is this so important? Well, the reason why you see so many of these normal distributions is because of a thing called the central limit theorem. I think I got to that. I mentioned this in my last video on the binomial distribution. It turns out it doesn't even have to be a binomial distribution. If you start with any statistical distribution you like, and you repeat it enough times. So for instance, I mean, a binomial distribution is just one example of that. But you could start with any distribution. For instance, the distribution of rolls of die or rolls of two dice. I mean, that's not a normal distribution. But if you do it enough times, if you keep repeating this experiment, keep adding the results or keep taking the mean of the results, you'll find that in the limit is which the number of trials you do goes to infinity, that the distribution, either of the mean or of the sum, is going to approach a normal distribution, and you can prove this result. And so here's what you get. I mean, and it's useful to work with this thing they call the standard score, which is written by the letter Z. So usually when you're working with data and one variable, the variable usually represent your data with is X. That's what's called an independent variable, something you're just measuring. Like that could be height of a group of people, could be weight, could be pretty much anything you're interested in studying. So usually you write x1, x2, x3, xi for the ith, um, the ith data point, the height of, if you like, of the ith person you're measuring. And mu is just the mean of all the data. And sigma, like I said before, is a standard deviation. If you have a sample or a population standard deviation, that usually goes by the letter sigma, but that's like a sum. So you want to always divide that by the square root of n. That gives you what's called the standard deviation of the mean. That's why we're dividing by the square root of n here. It turns out that the more and more data you collect, the distribution you get of the mean it gets narrower and narrower. Um, so that's why you have the sigma over square root of n. But it does approach a standard normal distribution if you repeat it enough times. And here's the exact formula. And like I said, Carl Friedrich Gauss discovered this formula. This formula looks pretty ugly. You'll see that it simplifies if you represent it in terms of the standard score. So I think it's a pretty remarkable formula. I mean, let's not worry about this form because it's kind of a complicated form. But if you use a standard score, then the formula simplifies quite a bit. So if you use like z equals x minus mu over sigma, which is what I showed you before, then the distribution of the standard score has this kind of simple form. It's 1 over square root of 2 pi. This is the normalization factor. And I think it's kind of interesting that you get something involving a square root of 2 pi. I mean, this is the first formula I ever saw that involved a square root of pi or square root of a multiple of pi, and I was kind of mystified by it. Um, you see pi a lot in math, and this doesn't even there's no obvious connection with circles here. Uh, but like I said, it's a normalization factor. The important part here is this factor to the right, e to the minus z squared over 2. That gives you the bell shape. And I think it's kind of easy to see this. I mean, e to the x is what's called an exponential function. Notice it has a negative argument, minus z squared over 2. That means when z is 0, this thing is 1. But as z increases, this factor on the right gets small. And it gets small pretty fast. I mean, z is the number of standard deviations away from the mean you are. So when z is 1, you have e to the minus 1 half, which is about 0.6. So that means that the height of the bell curve is about 0.6 as maximum, 0.6 times as maximum when you're one standard deviation away. But if you're two standard deviations, then the square is now 4. So now you have e to the minus 2. That's already like about 1/7. So by the way, by the time you're two standard deviations away from the mean, your height of the curve is only about 1/7 maximum. That's why you don't get much data beyond two standard deviations. This keeps getting bigger and bigger, the z squared over 2. So the factor e to the minus z squared over 2 gets very small very fast, and it gives you the characteristic bell shape. Anyway, here's a picture. So, I mean, this looks, pretty much exactly like the picture I showed you earlier, where I was actually showing you regular data. But since we're working with z here, now it becomes what's known as a standard normals distribution. So the mean in this case is 0. The mean and value of z is 0. Z equals 0 just means you're at the mean. And z, the value of z really just tells you how many standard deviations above or below the mean a given data point is. So you know that 68% of your data lies between z equals -1 and z equals +1. About 95% of your data lies between z equals -2 and z equals +2. About 99.7 between z equals -3 and z equals +3. And this is kind of a hard thing to work with. Usually interested in in determining areas under portions of the standard normal distribution. This is when if you want to know like what percentage of your data lies between two values. First you have to convert them to standard scores, and then you have to compute this area. And it's not an easy area to compute. There is a function that does this. It's called the error function, but it's not an easy thing to calculate. I think there are calculators that do it now, but the kind of classical way to do it is use something called a standard normal distribution table. And most people that deal with statistics and normal distributions have to use this table. And you can use this table. I'm not going to do it here, but you can use this table to determine, what percentage of your data lies within some interval of standard scores. And you can go back from standard scores to the value of x in your data. So you can know, for instance, what percentage of your population has a height, say, between 160 and 170 centimeters. You can do nice things like that if you have a normal distribution. And there's just one more thing I want to mention here, IQ. IQ is actually, I learned this just a few years ago. I mean, IQ stands for intelligence quotient. And for children, it's pretty easy to determine IQ. It's a quotient, and I think the way they calculate it, it's your mental age divided by your actual age. So, for instance, say you were 12 years old and you were as smart as a typical 15-year-old. So then your IQ would be 15 over 12, which is 125. If your mental age is the same as your actual age, then your IQ is 100, and if it's lower, then your IQ is less than 100. So that works for children. But what about adults? Well, the way we measure IQs of adults is we use a bell curve. We use a normal distribution. So what you do is you test a bunch of adults. You test like maybe several thousand. I mean, when they do these IQ tests, they usually calculate, test thousands, hundreds of thousands sometimes. I think there's probably even been some IQ tests where they've tested over 1 million adults. But what you get is you get this distribution, and I mean, some people score higher than others. Obviously, there's going to be a distribution in the scores, but you kind of normalize the distribution to get this bell curve, and then you say that your IQ is 115. I mean, your IQ is 100 if you're right in the middle. So if you score the mean on an adult IQ test, then that means you have an IQ of 100. But say you scored a one standard deviation above the mean. Well, then for most IQ tests, I don't know if this is absolutely standard, but for most IQ tests, the way they measure IQ is a standard deviation is 15. So if you're one standard deviation above the mean, that means you're 84 percentile. That means your IQ is 115. And if you're two standard deviations above the mean, that means that you're like 97 percentile. That means you're pretty damn smart. That would mean your IQ is 130. And I think what most people call genius is like three standard deviations or more above the mean. So that'd be like 145. I don't know. I don't think it's an absolute convention. Some people say 150 or higher is genius. And IQ is pretty misleading. I mean, I don't really like IQ tests that much because you're assigning one number to someone's intelligence, which I think is very, very misleading. I mean, there's a lot of different aspects of people's intelligence, and I mean, I don't think you can test all of them. I mean, I think IQ tests are also misleading because I don't think we really measure how smart people are. I mean, you're measuring basically how well you can perform on one of the Binet tests, and I think they are biased. They think they're culturally biased. I don't want to get into that too much, but this is just an example of where you might use a normal distribution. And there's a lot of other uses for normal distributions. There's also a lot of other commonly used distributions and statistics. I'll get to some of them probably later in this series. But anyway, that kind of concludes my talk for today on normal distributions. I hope you enjoyed it. Thank you for watching, and long live math. And I'll see you next time.